Welcome to part 7 on rational functions. We're going to graph h of x equals x plus 2 times x squared minus 9 all over x squared minus 4. We will factor this first. This will give me x plus 2 times x plus 3 times x minus 3 all over x plus 2 times x minus 2. Dividing out the common factor, which will give me a removable discontinuity, I will now have the function h of x equals x plus 3 times x minus 3 all over x minus 2, where there is a hole at x equals -2. To find the y-coordinate of this hole, we take h of x and we substitute -2 in to find the y-coordinate. H of 2 will be -2 plus 3 times -2 minus 3 all over -2 minus 2. Simplifying gives me 1 times -5 all over -4. So I have a coordinate point for a removable discontinuity at 5/4. So the coordinate point for the hole is -2, 5/4. There is a vertical asymptote at x equals 2, and there is an oblique asymptote of degree 1 because the degree of the numerator is greater than the degree of the denominator by 1 degree. So to find the equation of the oblique asymptote, we take the numerator, which is x squared minus 9, and we divide it by the denominator, x minus 2. Since the degree of the denominator is 1, we can use synthetic division. This will be coefficients 1, 0, and -9, and the number I'm dividing by will be a 2. If I drop 1 down, I get 2 times 1, which is 2. 0 plus 2 is 2. 2 times 2 is 4, and -9 plus 4 is -5. My remainder is -5. So the constant term is 2, and the equation of my oblique asymptote will be y equals x plus 2. Note that the remainder is a -5 divided by x minus 2. The whole thing will approach a very small number, in which case we disregard it. So now we have checked for removable discontinuities, vertical asymptotes, oblique asymptotes, and now we need to check if there are any points on the x or y axis that the function crosses. If we let y equal 0, we can find the x intercepts. These are the roots or zeros of the rational function. We can find those by looking at the numerator. So we have x equals -3 and x equals 3. These are the zeros or roots. This is where the function will cross the x-axis. If we set x equal to 0, we can find the values of y or y-intercepts. This will be at 3 times -3 times -2, which is at -9 over -2, or simply 9/2. So the coordinate points we have for roots are -3, 0, and 3, 0. And the coordinate points we have for y-intercepts are just 1, 0, 9/2. The last part of this process is to find where the rational function is positive and negative. We can do this with a quick sketch of all the binomial factors. We have an x plus 3, we have an x minus 3, and we have an x minus 2. That means we would have a cubic. There will be zeros at -3, +3, and 2. We know the general shape of a positive cubic comes in from the bottom left and leaves from the top right. This means that where the function is below the x-axis will be negative, and where the function is above the x-axis will be the positive interval for the rational function. And again, this is only true because the rules for multiplication and division on signed numbers are the same. And so this tells me where the function will be positive and where the function will be negative. That's all this does. This is just replacing a sign chart. So my interval that is negative is from -infinity to -3, and from 2 to 3. That's the interval that's negative. The interval that's positive is from -3 to 2, and also from 3 to infinity. We now have all the information we need to graph this function. First, I'll list the vertical asymptotes at 2. Then I will list the horizontal asymptotes if they exist, which they don't. So now I move on to oblique asymptotes. The oblique asymptote is at x plus 2. So I have a rise of 1, a run of 1, a rise of 1, a run of 1. We'll make this oblique asymptote a diagonal dotted line. I'm now going to color in the zeros or roots of this rational function. They are at -3, 0, and at 3, 0. And I'm also going to list where the holes on this function exist. So the holes exist at -2, 5/4, which is just over 1. The last thing I'm going to do is highlight in green the portions of the rational function that are positive, and I'll highlight in red the portions that are negative. So this tells me where my rational function will exist. I know my function has to be negative to the left of -3. I know it has to cross at -3 because it is a 0 of the rational function. I also know it cannot exist at -2, 5/4, and I also know that it must hug this vertical asymptote at 2 to positive infinity. I know that my function is negative anywhere between 2 and 3, but it has to cross at 3. And my function has to hug the oblique asymptote to positive infinity, which means the blue line I'm sketching will approach the diagonal or oblique asymptote. The very last thing we'll do is identify where the rational function crosses the y-axis. And we found that already to be at 0, 9/2. So that is this point right here. It's where the curve between -3 and 2 crosses the y-axis at 0, 9/2. And that's pretty much it.